Welcome back to the workshop. This session is a continuation of Module 5 on the rigid pavement design strategies and transfer functions. Module 5.1.2 focuses on and discusses Jpcp joint faulting. For transverse joint faulting in jointed plane concrete pavements, the same type of information will be discussed as was included for med slab fatigue cracking of jointed concrete pavements. There are three learning objectives of this module on transverse joint faulting, which include: the first is to define and explain faulting of the transverse joints of jointed plane concrete pavements. The second is to define the incremental faulting damage concept used to predict faulting of the transverse joints. And the third is to describe the transfer function or model for the faulting of the jointed plane concrete pavement transverse joints. Just like for the jointed plane concrete pavements med slab fatigue cracking, joint faulting is grouped into three sections: definition and measurement of joint faulting, the distress mechanism integrated in the pavement ME design software, and the transfer function or model for predicting joint faulting over the design period. We'll start with the definition and measurement of transverse joint faulting. Faulting is defined as a difference in elevation of the slab's edge across a transverse joint, which is measured about 12 inches from the edge of the slab. Faulting can be measured manually, which is more accurate, or using high-speed laser technology, which is becoming the more common. The mean joint fault is calculated from measurements across multiple transverse joints within the analysis section. This photo is a close-up of the concrete slab edge showing the difference in elevation between the approach and the leave slabs of the transverse joint. As noted in the previous slide, faulting is measured 12 inches from the edge of the slab or from the edge paint stripe where widened slabs are used. Faulting can occur along mid-slab fatigue cracks, as shown in this photo, but only faulting along the transverse joints are predicted by the pavement ME design software. A point to remember: faulting has a significant impact on the measured IRI values. The pavement ME design software, however, only uses the faulting predicted along the transverse joint to estimate the IRI along the project. Now let's overview and discuss the distress mechanism for predicting faulting of transverse joints. Faulting is a result of repeated heavy traffic loads that cross a transverse joint, causing a differential deflection between the loaded and unloaded slab edges at the transverse joint. The differential vertical deflection is defined as the deflection of the loaded slab minus the deflection of the unloaded slab. There are 5 key factors that cause or correlate well with the differential deflections across the transverse joint. The differential deflection is a critical response parameter used to predict faulting of transverse joints. The first factor is the application of repeated heavy axle loads. The second is the upward curling of the concrete slab. The third is the erodibility of the underlying base or subbase layer and subgrade from pumping of fines. The fourth, which is tied to the third, is free water beneath the slab in the base, subbase, and or subgrade layers. In other words, the higher the water content of the underlying or supporting layer, the greater the faulting. The fifth is a poor joint load transfer efficiency across the transverse joint. Remember, the Pavement ME design software does not predict the faulting of mid-slab transverse cracks. The next slides will overview the key factors or mechanisms that cause faulting. Remember, it is a combination of these key factors that define the magnitude and rate of faulting predicted by the Pavement ME design software. Starting with the first two key factors, the combination of repeated heavy axle loads with the upward curling of the slab corners. The photograph in this slide includes a string stretched diagonally across the slab from one corner to the opposite corner of the slab. The shadow of the string shows the PCC slab is curved upward. The PCC slabs are curled upward much of the time. The upward curling of the slab, combined with the repeated application of heavy axle loads, contributes to higher differential deflections and the increase in potential for pumping and erosion beneath the concrete slab. This slide schematically illustrates the result of the pumping and erosion action correlated to faulting. In other words, the erodibility of the underlying materials beneath the concrete slab combined with the repeated application of heavy axle loads. In summary, the moving axle load approaches the transverse joint and deflects the approach slab of the transverse joint over time, which is dependent upon the truck speed. The axle load crosses the joint and suddenly loads the leave slab side of the transverse joint. This sudden action causes the material, fines and water, under the leave slab to erode and move backwards from under the leave slab to the approach slab. The material accumulates under the approach slab, lifting it up and causing faulting. The photograph included in this slide shows severe pumping and erosion of material beneath the PCC slab along the edge of the slab itself. The pumping and erosion of the underlying materials can also occur along the transverse joint. The higher the water content in the underlying or supporting layers beneath the concrete slab, the higher the probability of pumping and erosion for certain base layers and subgrade soils that have greater amounts of fines. Another point to consider or to remember relative to the fatigue cracking of the concrete slabs, when pumping and erosions occur beneath the concrete slab, that increases the potential for mid-slab fatigue cracking because the tensile stress at the bottom of the slab and top of the slab will increase, reducing the allowable number of load applications and increasing the potential or probability for mid-slab fatigue cracks. The fifth factor, highly correlated to joint faulting, is the low transfer efficiency of the transverse joint in combination with the repeated application of heavy axle loads. Remember from an earlier slide within this module, the differential deflection is deflection of the loaded side of the slab minus the deflection on the unloaded side of the slab. The load transfer efficiency is defined for jointed plane concrete pavements as the ratio of deflection measured at the corner of the unloaded slab divided by the deflection measured at the corner of the loaded slab times 100 for a percentage value to report the load transfer efficiency as a percentage value. A factor that has a significant impact on the load transfer efficiency is the width of the transverse joint. The wider the transverse joint opening, the lower and higher degradation of the load transfer efficiency over time with repeated applications of heavy axle loads. In other words, the ratio of the unloaded slab, deflections of the unloaded slab divided by the deflections of the loaded slab start to decrease. So the load transfer efficiency decreases. This slide includes a schematic illustration of the load transfer efficiency for two extreme conditions. The first is when no load is transferred across the transverse joint, so the differential deflection is equal to the deflection of the loaded slab, and the load transfer efficiency is basically zero. The condition is approached when dowels are not used and the width of the joint is higher or greater for whatever reason. The second is when all of the load is transferred across the transverse joint. So the transverse joint is simulating the interior slab condition, and the deflection of the unloaded slab is equal to the deflection of the loaded slab. So the differential deflection is zero and the load transfer efficiency is 100%. This condition is approached when dowels are used in the transverse joint and the width of the joint is very low or very tight. A tabular summary is included in this slab that simply provides a verbal description of the different load transfer efficiency ratings. More than 90% is considered excellent, and the resulting faulting will be very low or nil. A LTE value ranging from 70 to 90% is considered good, and the resulting faulting should be low. A LTE value ranging from 50 to 70% is considered fair, and the resulting faulting will be high. An LTE value less than 50% is considered poor, and the resulting faulting will probably be excessive. Obviously, the faulting is heavily dependent on the number and magnitude of axle loads, as well as the other 4 factors previously discussed. Now let's move or discuss the specific model used to predict faulting over time. This flowchart or diagram is a simplified version of the process and faulting prediction model included in the Pavement ME software. This next section will identify and overview the critical responses and their location in calculating faulting over the design period. The critical responses include the calculated joint opening or joint width and low transfer efficiency of the transverse joint. The width of the joint will increase over time as a result of shrinkage of the concrete slabs. The deflections calculated on the loaded and unloaded side of the transverse joint, the differential energy across the transverse joint. The differential energy across the transverse joint will be defined later within this section of the module. Remember from Module 2, ISLAB 2000 is used to calculate the responses of the concrete slabs for designing jointed plane concrete pavements. ISLAB 2000 is a finite element program. Millions of runs were made with ISLAB 2000 to calculate critical rigid pavement responses, which were used to create the artificial neural networks embedded within Pavement ME design software. The artificial neural networks in the Pavement ME software are used to calculate the critical responses for predicting faulting of the jointed plane concrete pavements. So the jointed plane concrete pavement responses are calculated with the artificial neural networks and not directly with ISLAB 2000 itself. The rigid pavement responses of slab deflections are dependent on the wheel loads and their locations, the temperature gradients through the concrete slab, and the properties of the pavement layers and subgrades supporting the concrete slab. These critical pavement responses of flat slab deflections are used to predict faulting of the transverse joints. The critical location of the deflections or responses is at the corner of the slab along the edge of the pavement. The deflections on the loaded and unloaded side of the transverse joint are calculated. Each of the axle loads are moved adjacent to the transverse joint for calculating the deflections to predict the faulting resulting from each axle configuration, including single, tandem, tridem, and quad axles. In summary, or as an overview, the axle or wheel loads are placed at or near the corner of the slab. The temperature gradient that causes curling of the slab is calculated, that is dependent on the time day and other factors. The base and other layers below the slab are used to determine the composite K value in calculating the corner deflections of the loaded and unloaded concrete slabs. The load transfer efficiency of the joint is calculated through the aggregate interlock and dowel diameter if dowels are present. ISLAB 2000 calculates deflection of loaded and of the unloaded sides of the joint, determining the differential deflection. The differential deflection is directly used to predict faulting of the transverse joints. For Module 2, the faulting prediction model is referred to as a direct transfer function for which the differential deflection is directly correlated to or used to predict faulting. The next slides will illustrate the difference between undowed and dowed transverse joints. First, for undowed joints, the critical response of the differential deflection calculation location is near the slab corners as displayed in the previous slide and in this slide. The low transfer efficiency degrades over time and is dependent on the width of the joint, aggregate interlock, magnitude and number of axle loads, bonding or the interface friction between the PCC slab and underlying layer, the supporting base resilient modulus and its potential for pumping and erosion, and the magnitude of free moisture and resilient modulus of other supporting layers, including the subgrade. For doweled joints, the critical responses in their locations are the same as for undoweled joints. The difference for the dowel joints is the dowels increase the joint load transfer efficiency, which reduces the differential deflection across the transverse joint. An additional critical response variable for the dowel joints that impacts the load transfer efficiency is the dowel concrete bearing stress with the differential deformation or deflection, or the density of energy of the subgrade. Now that we've reviewed the distress mechanism, this session will overview the model and/or transfer function to calculate faulting over the design life of the jointed plane concrete pavement. From Module 2, the faulting prediction model is referred to as a direct transfer function for which the differential deflection is directly correlated to and used to predict faulting. Coming back to the overall faulting model, flow chart or diagram. Mean joint faulting is predicted using an incremental approach. A faulting increment is determined each month or time increment, and the current faulting level affects the magnitude of the increment. The faulting at each month is determined as the sum of faulting increments from all previous months in the pavement life combined with the additional traffic applied in the next increment of traffic and change in properties of the concrete slab and underlying support layers. The total faulting is calculated by summing all of the incremental faults. In summary, faulting is accumulated over the design period. The design period is divided into time increments, and the changes to the pavement and site factors are determined for the specific time increment. The pavement and site factors considered within each increment include the concrete flexural strength and elastic modulus, moisture gradients throughout the slab, hourly temperature gradients through the slab, traffic variations of each axle type and load, transverse joint opening or width on a monthly basis, joint load transfer on a monthly basis, base layer erosion or the loss of support, and subgrade support and erosion or loss of support. This slide includes an overview of the incremental faulting calculations, which is directly tied to the differential deflection or differential density, defined as dE, of the subgrade across the transverse joint. So the total fault is simply equal to the accumulation of the incremental faults. The incremental faults is defined by the change in the fault during month I from the previous month, or I minus 1. The maximum fault means the maximum mean faulting for the previous month. The differential deformation energy, defined as dE, is accumulated during month I and depends heavily on the load transfer efficiency. First, let's define the coefficient C34. This coefficient is related to the base freezing index, or the FR term, the base freezing index, or FR term. The base freezing index is defined as the percentage of time the top base temperature is below freezing. For the time increments when the base temperature is always above freezing, the C3 coefficient of 0.005 and the C4 constant of 0.00444 applies to all incremental faulting computations. The values for the calibration coefficients may vary between different publications of the MEPDG Manual of Practice, depending on the results from any updated global calibration. The coefficient and exponents of the transfer function are also included in the output report for the Pavement ME design software. Next, let's define the differential deformation or energy variable. The DEI is the differential deformation or differential density of energy of the subgrade imposed by an axle load. The differential density or energy of the subgrade is defined by the density or energy of the subgrade under the loaded and unloaded sides of the transverse joint, as defined in the above equation. In other words, the density of energy of subgrade imposed by the loaded slab minus the density of energy of the subgrade imposed by the unloaded slab. The closed form solution of the differential density of energy of the subgrade is included on this slide and is highly correlated to the loaded and unloaded deflections at the slab corners on different sides of the transverse joint. The differential density of energy of the subgrade depends on the load transfer efficiency across the transverse joint. Remember, the load transfer efficiency is calculated by the equation displayed on this slide, which was previously discussed within this section of the submodule. The load subgrade differential density of energy is dependent on the base and subgrade layer stiffnesses or modulus values, and the load transfer degradation or deterioration due to a loss of aggregate interlock, and the effectiveness of the dowel stiffness or damage of the dowel concrete interface or bearing stress. The deterioration of the joint load transfer as a result of loss in aggregate shear capacity and dowel damage are both modeled in the pavement ME design software. The overall load transfer efficiency of the transverse joint is critical in calculating faulting over the design life of a jointed plane concrete pavement. Load transfer efficiency is defined or determined from three components of load transfer efficiency. Those three components are aggregate interlock, the use of dowels, whether dowels are present, and the base subgrade support relative to load transfer efficiency. The combination of all load transfer efficiency factors is used to calculate the load transfer efficiency of the transverse joint at a specific point in time. The load transfer efficiency from the aggregate interlock depends on the joint opening or width, and it deteriorates with the application of wheel loads throughout the design period. The load transfer efficiency from the use of dowels depends on the dowel diameter and spacing. With appropriately sized dowels, the load transfer efficiency remains relatively constant over time after the initial deterioration. The load transfer efficiency from the base layer depends on the base type and stiffness or modulus, resilient modulus, and the base layer thickness. The load transfer efficiency component from the aggregate interlock is dependent upon the loss of shear capacity. The loss of shear capacity is dependent on repeated axle load magnitude and number of load applications, the reference shear stress, the transverse joint width or opening that varies with season and time, the concrete slab stress, thickness, concrete slab thickness, and the shear stress on the transverse cracks by an axle load group. The shear stress will be defined on the next slide. As noted on the previous slide, the load transfer efficiency component from the aggregate interlock is dependent upon the shear stress on the aggregate faces along the corner of the transverse joints. The shear stress is calculated by the equations included on this slide from the aggregate interlock stiffness factor, the slab thickness, and the corner deflections of the loaded and unloaded slabs. Two graphs are displayed on this slide. The left graph illustrates the change and decrease in load transfer efficiency calculated by the Pavement ME design software for a jointed plane concrete pavement without dowels over pavement age. As displayed, there is a significant change in load transfer efficiency throughout the design life and throughout a year or climate section. The graph on the right side illustrates the change and decrease in load transfer efficiency for the same jointed plain concrete as for the graph on the left, but with appropriately sized dowel. As shown, the load transfer efficiency initially decreases but then remains relatively stable throughout the design life. The difference in the load transfer efficiency contributed by the aggregate interlock between the two is significant, as shown. The use of dowel reduces the shear stresses exhibited on the aggregate surface so that the degradation of load transfer efficiency contributed by aggregate interlock is much less throughout the design period for the pavement with dowels. The load transfer efficiency component from the use of dowels in the transverse joint is determined through a dowel damage factor. The dowel damage factor is calculated using the equation included on the slide and includes the following variables. The JD is a non-dimensional dowel stiffness at the time of the load application. The lambda L and U is simply the corner deflection of the loaded and unloaded slabs. The DSP is the space between adjacent dowels. The D is the dowel diameter. The F'C is simply the concrete compressive stress. And the C8 value or coefficient is a calibration coefficient of damage and is equal to 400. This slide includes graphs relating the effectiveness of the dowel to retain a high load transfer efficiency throughout the design period, and basically compares a slab with an appropriately sized dowel versus another slab with an inappropriately sized dowel for the slab thickness and traffic. A dowel diameter that is too small for the level of traffic and slab thickness, say a 1-inch dowel diameter, will exhibit higher bearing stresses and result in much lower load transfer efficiency values predicted over time in comparison to a dowel diameter of 1.5 inches as displayed in this graph. With the higher bearing stresses, the dowels become loose, resulting in higher differential deflection and more faulting predicted for the transverse joint, as displayed in the lower graph comparing the 1 inch to the 1.5 inch dowel diameters. The 1-inch dowel diameter versus the 1.5 inch dowel diameters. The long-term efficiency of the dowel bars is dependent on the magnitude of the dowel concrete bearing stress, as noted in the previous slides. Excessive bearing stress will lead to fracturing of the concrete, the occurrence of dowel socketing, and poor load transfer. The poor load transfer will lead to higher differential deflections across the transverse joint. Remember, higher differential deflections result in higher faulting predictions because it is a critical response variable. The report in the Pavement ME software includes a plot of load transfer efficiency over the design period, as displayed in the graph. The minimum load transfer efficiency suggested over the design life for low faulting values is about 90%. The incremental faulting approach starts with calculating the initial maximum fault for each month, which is dependent on selected site factors, including subgrade and climate, and the erodibility of the base layer and or subgrade. The increase in faulting is calculated by the subgrade differential density of energy and the erodibility factor calculated within the time increment itself. The terms in the incremental faulting approach are listed and defined on the slide and include basically fault max is the maximum mean faulting for month I. Fault max 0 is the initial maximum faulting for month I. EROD is the base erodibility factor. The DE is the subgrade differential density or energy accumulating for month I. The curling is simply the maximum mean monthly slab corner upward deflection due to temperature and or moisture curling. The PS is overburden of the subgrade. P200 is a percent subgrade material passing the number 200 sieve, and the number of wet days is the average annual number of wet days that are greater than 0.1 inches of rainfall. The calibration coefficient for the incremental faulting approach are designated on this slide. The value of C5, the calibration coefficient, is 250. C5 of 250. The value for C6, calibration coefficient, is 0.2, and the value of C7, calibration coefficient, is 20. The values for the calibration coefficients may vary between different publications of the MEPDG Manual of Practice, depending on the results from any recent global calibration. The coefficients and exponents of the transfer function are also included in the output report for the Pavement ME Design software. In summary, the incremental or the initial maximum faulting value at the beginning of the time increment is a function of the subgrade and climate variables and the curling of the concrete slab as defined on the previous slide. The final maximum faulting value at the end of the time increment is a function of the subgrade differential density of energy across the transverse joint and the erodibility factor, as well as the magnitude of the initial maximum faulting value. The faulting within each of the time increments are summed to determine the total faulting of the transverse joints. Now let's define the coefficient C12 within the maximum faulting or within the incremental faulting approach. This coefficient is related to the base freezing index or the FR term. The base freezing index is defined as the percentage of time the top base temperature is below freezing. For the time increments when the base temperature is always above freezing index, the coefficient C1 is 0.2, and the C2 coefficient is 1.636, which applies to all incremental faulting computations. The values for the calibration coefficients may vary between different publications of the MEPDG Manual of Practice depending on the results of the calibration. The coefficient and exponents of the transfer functions are also included in the output report for the Pavement ME design software. Remember from Module 2, the critical pavement responses are used to determine or calculate incremental faulting, and the direct transfer function or model converts the faulting damage to what we can see or measure on the pavement surface, the faulting of the transverse joint. So the critical response variable is deflections across the transverse joints on the loaded and unloaded side of the transverse joints. In summary, the differential deflection from the low transfer efficiency and the differential density of energy of the subgrade are used to directly calculate average faulting of the transverse joints. This slide simply summarizes the calibration coefficients that were used to calibrate or from the calibration of the direct transfer function or model in predicting total faulting throughout the design period. The calibration coefficients are from C1 through C8 as displayed on this slide. As noted previously, the values for the calibration coefficients may vary between different publications of the MEPDG Manual of Practice depending on the results of any recent global calibration process. The coefficients and exponents of the transfer function are also included in the output report for the Pavement ME design software. Reliability was discussed in detail in Module 3 and how it is applied in the Pavement ME design software. The standard deviations of the residuals for faulting is displayed on this slide. The standard deviation of the residuals is used to determine the reliability as related to the faulting of transverse joints in jointed plane concrete pavements. This final section is a summary of the materials presented under Module 5.2.1 for the faulting of transverse joints. In summary, we defined and explained faulting of transverse joints in jointed plane concrete pavements. We also defined the incremental faulting concept used to predict faulting of transverse joints. And we also described the transfer function for the faulting of transverse joints in jointed plane concrete pavements. This ends Module 5.1.2 on transverse joint faulting. The next submodule of the training course sequencing is Module 5.1.3 on the jointed plane concrete pavement IRI or smoothness degradation.